So, as I just explained, so today we will be discussing the slicing procedures in layered manufacturing. Now, why slicing is so important? So, slicing is basically inducted into the basic concept of additive manufacturing, where when we described additive manufacturing, what we said was manufacturing process is simply a process where layer by layer deposition is going to take place. Now, when I say layer by layer deposition is going to take place, it inherently means that a solid object will be there and it will be cut into slices. So when I'm going to cut a part in slices, I have to understand two very important aspects. The first aspect is what should be the height of the slice. This is called as H. That is the height of the slice. This is the first part. And second part is where should I slice? What will be the height of the slice? That is the first question. And the second question basically is going to be, where do I slice? Because what happens is, if I have a product like this, now if I go for uniform slicing, what happens over here is I get a slice over here like this. I get a slice like this. So what happens is this slice contains a critical feature. So where do I slice? So if I slice like this, I can save the critical feature. But suppose if I slice like this, the slice is cutting exactly through the critical feature. So the question becomes very pertinent as to where do I slice and what will be the height of my slice. So in layered manufacturing, slicing of the CAD model of a part to be produced is one of the most important steps, because slicing of a CAD model also affects the three basic criteria of additive manufacturing, that is time, surface finish, and the third most important aspect, that is orientation. So if I take thin slices, like if I assume this slice to be say 100 micron. Okay, now let us assume I take a 50 micron slice. I take a slice of 50 microns. So now the number of slices are going to go up. So rather than having only 2 slices over here, I will now have 4 slices. So definitely the time of deposition will definitely increase. Now if time of deposition increases, what happens is the overall time in developing the product is going to increase. So the build time, this is what we call as the build time, it increases. The build time is going to increase. Okay. Now on the contrary, let's assume that this part has a slice of 50 micron. This part has a slice of 50 micron. And now what I want to do is, I want to create a part with 100 micron. So if I'm making a part which is like this, like a cube to be very precise, if a part is like a cube, it will have no effect. Okay, but if I have a part like this, now if I make a dimension, the part is going to be fabricated something like this. So now when the layer height increases, what happens is the surface finish deteriorates. The surface finish deteriorates because what you start to observe over here is what we technically call as staircasing. Everybody must have seen stairs. So as you move across the stairs, what you can observe is there is a flat surface and a height, then a flat surface and a height, then a flat surface and a height. So like this, if you move a surface roughness probe across this, so this is the region where you will get surface roughness. This is the region where you will get surface roughness. So Now, the problem over here that you encounter, over here that you will basically encounter is which of the two criteria you are going to keep as your first or the important criteria. So that basically is dependent upon the importance of slicing process. That is basically dependent on the importance of the slicing process. So as I just explained, there are two contradicting issues. Now build time is and surface quality. So what in ideal scenario, your objective is to minimize the build time and maximize the surface quality. That is your objective during normal scenarios. But when you go for slicing procedure, you have to be very, very clear in your head. Out of these three, this is one criteria, this is the second criteria, and this is the third criteria. Out of these three, which is going to be your primary criteria, which is going to be your secondary criteria, and which is going to be your third criteria. So as I explained earlier also many times, like if I want somebody to just see the part, it is only for visual demonstration. It is not for any use, or it is not for any application. It is just for visual demonstration. In that case, build time is my criteria, because I want to make the part faster. Simply, I want to make the part faster, aesthetically meaningful. Doesn't mean a lot to me, aesthetically meaningful, because I'm just trying to show the part to somebody. So in that case, build time becomes my criteria. So for minimizing the build time, what happens? The layer thickness is increased. For minimizing the build time, layer thickness is increased. Now, on the contrary, if suppose I am making a part which is a component of an assembly. So assembly means it has to fit properly. So the tolerance available to me is very less. The tolerance that is available to me is going to be very less. In that case, surface finish becomes my primary criteria. So in order to maximize surface finish, the layer thickness has to be decreased. So the moment I decrease layer thickness, build time is going to increase. So every process over here basically leads to a contradiction of a sort between quality and time. These are the two primary criteria that I have to juggle along during the slicing process. So now when you talk of slicing process, let us first understand how the part is actually fabricated. Now, if you go and observe these parts under microscope or a profile projector, what you would observe is that the parts are actually fabricated like this. Actually, the part has a specific layer height. This is called as the layer height, or LT, that is the layer thickness. Every layer thickness you can define individually also. Theoretically, you can define every layer thickness individually also in order to get the profile. So this is called as the profile. This is the profile that I want. So based on this profile, what has happened is number of layers have been plotted. So in RP, if you remember the process of RP, what happened was we had a CAD model, we sliced the CAD model, and then we squared off the edges. So squaring of the edges actually leads to this effect. The squaring of edges actually leads to this effect, and this effect is called as staircasing effect. Okay. So when you get a staircasing effect, definitely you are going to get surface roughness. If you move your probe across this profile that you have, if you move your probe across this profile, what will happen is there are peaks and there are valleys. So this is a peak and this is a valley. So again, this becomes a peak and valley for this system. So for this system, this becomes the peak and this becomes a valley. So every time there is a peak and valley, when you move your surface roughness probe across this line, what you would observe is surface roughness data being generated. Now, when you start to observe this thing, you have to understand the reason of surface roughness is two-pronged. The basic reason of surface roughness is two-pronged. What is those two? Layer height is one of the primary reasons. Layer thickness is one of the primary reasons of generating a surface roughness. In an RP system, surface roughness can never be eliminated. You will never have a perfectly plain surface. You will never have. So surface roughness can be minimized, but it cannot be eliminated. So when we talk of minimization of surface roughness, what are we talking about? Minimization of layer thickness. We are talking about minimization of layer thickness. So minimum layer thickness, minimum surface roughness. So that is the concept. Now, when I look at this figure, what do I see over here? I see something like this, a triangle being formed. So this is the layer thickness. I have just extended this figure, and this is what we call as the overhang. This is what we call as the overhang. Now, if I take this vertical surface normal and project it backwards, so this is the surface normal. This is the surface normal. This is the profile. Okay. So if I just project this surface normal back, this triangle is the source. This triangle is going to be the source of any potential surface roughness that is being developed. This height is called as cusp height. And for theoretical purposes, cusp height is assumed to be the surface roughness of the facet generated due to layering. So when I talk of cusp height, I'll start discussing cusp height from the next slide onwards. So you need to understand what is the cusp height. So cusp height is basically defined as the distance from the connecting point of layer and overhang to the surface normal projecting on the profile line. So what is cusp height? Cusp height is the radial distance or the linear distance from the junction of layer thickness and overhang towards the surface normal on the profile line. So this is what we call as the cusp height. And for theoretical assumptions, what we assume is the cusp height is directly related to the surface roughness of the facet that is being generated. Now, what is a facet? So this triangle over here, that is a single facet. This triangle over here, this triangle is a single facet. This triangle is a single facet. So now another point of discussion comes into picture. Now suppose you have a sphere, basically you have a sphere, and now you want to slice that sphere into slices. So you decide on the slice thickness, everything. So layer thickness is something decided, let us say X for this value right now. Now you have decided the layer thickness. Now a very important and a pertinent question comes with respect to the staircasing that is bound to happen. Now where do you want the staircasing to happen? Now as you can see, this is the profile. This is the profile of the sphere. Now where do you want the staircasing to happen? So people did a lot of research in this aspect, and they actually came out with multiple options. So the first option was that all the slice heads were actually on the outside of the profile line. All the slice heads are on the outside of the profile line. That you can very easily see. The slice heads are coming outside. So the surface roughness actually is going to be generated outside the profile line. So the surface roughness is actually going to be generated outside the profile line. Two effects are bound to happen over here. First effect is, if you are using a plastic or even if you are using a metal, it will contract after solidification. It will contract after solidification. So there's a very good chance that after contraction, your profile line and your desired dimensions may be similar. That is, there is no deviation of dimensions. Dimensional inaccuracy is not present. But there is another option which might happen. Since the profile line is inside and the surface roughness is on the outside, when contraction happens, the contraction may not actually happen as per your understanding or as per what you desired. Therefore, your part is actually oversized. The part is actually oversized, or it can be undersized also. If it is oversized, no problem, you can go for post-processing. But if it is undersized, you have no other option except to throw this away and do the processing once again. So that is one option of external slicing. All the slices are outside. This is what we call as external slicing. Now the same option, but with a different perspective. Here, all the slices or the surface roughness profile is coming inside the profile line. Inside the profile line. So this is your profile line and all the surface roughness is happening inside the profile line. Now, theoretically, this is possible. I'm not saying practically this is feasible. I'm saying theoretically this is possible. So this actually gives me a very good idea that all the profile line actually incorporates your surface roughness. So you will have a defined surface roughness which will be desirable, but not optimal. It will be desirable, but not optimal. But the problem with contraction is that if it contracts, you are already at the outer periphery of your profile line. And if it contracts, what you will end up with is a part which is below the required dimensions, a part which is below the required dimensions, which cannot be taken care of, So what happened was, after some researches, people came up with a very novel idea. Now, what is this novel idea? I'll just explain to you. What people did was, you have a sphere and you have the profile line. You have a sphere and you have a profile line. Okay. Now, exactly at the center of the sphere, you draw a line. You draw your line. This is your center. This is your center. Now, what you do is, there are two zones. In this sphere, there are two zones. This is the first zone and this is the second zone. This is the second zone and this is your first zone. So in the first zone, your layers are actually going to come outside. Your layers are actually going to come outside. And in the second zone, which is your top zone, which is your top zone, the layers are actually going to come on the inside. So what is going to happen is, this is your profile that you wanted, and this is the actual profile that you got. So basically what you are doing is, you are trying to minimize the shrinkage of both the sides. I'm achieving the same amount of shrinkage by changing the philosophy of the part. So outer part will be on the outer side of the profile line, whereas the inner part will be inside the profile line. So you will end up having a product which will be not, I won't say it will be an exact replica, but it will be distinctly similar to the product that you actually wanted to use. So there are three basic ideas of slicing, where the slicing should lie. So the first idea is that all the slices should be outside. That is, the corner edges should be outside the profile line. The second is all the slices should be inside. That is, all the profile edges should be on the inside the profile line. And the third idea is you cut the object into half. One half should be outside the profile line and one half should be inside the profile line. And actually, after research, it was actually found that this idea, the third idea where the profile line is like profile is divided into two halves, actually gives me a more accurate description of the model as compared to either of these two ideas. So it gives me a better idea as compared to the other two ideas that were प्रोपोगेटेड। अब आते हैं स्लाइसिंग पे। तो जब हम स्लाइसिंग को बेसिकली हम क्लासिफाई करते हैं दो तरीके से, एक है यूनिफॉर्म स्लाइसिंग, एक है एडेप्टिव स्लाइसिंग। यूनिफॉर्म स्लाइसिंग क्या है कि जैसे सपोज ये पार्ट है, ठीक है, ये एक पार्ट है, ये पार्ट है, लेट अस अज्यूम 500 माइक्रॉन्स का ये पार्ट है। तो हमने क्या करा, इसको 5 लेयर्स में बांट दिया और हर लेयर की हाइट हमने डिफाइन कर दी 100 माइक्रोन। सो 100 माइक्रोन इनटू 5 लेयर्स विल गिव मी दी पार्ट। ठीक है, दिस इज कॉल्ड एज यूनिफॉर्म स्लाइसिंग। ठीक है, अब आते हैं एडेप्टिव स्लाइसिंग। व्हाट इज एडेप्टिव स्लाइसिंग? सेम कॉन्सेप्ट बट डिफरेंट आइडिया। हमारे पास एक पार्ट है जिसकी हाइट 500 माइक्रोन की है। अगर मैं इस पार्ट को ध्यान से देखूं तो यहां पर ना कोई सरफेस चेंजेस है, ना कोई डायमेंशनल चेंजेस है, ना कोई ज्योमेट्रिक चेंजेस है। ठीक है, नाउ व्हाट आई विल डू इज आई विल गो एंड चेक माय मशीन। आई विल गो एंड चेक माय मशीन सेटिंग। मशीन सेटिंग में मैं क्या चेक करूंगा कि मैं मैक्सिमम लेयर थिकनेस कितनी रख सकता हूं। ठीक है, सो नाउ व्हाट आई विल डू इज आई विल डिवाइड दिस इनटू 2 हाफ्स, take this as 250 micron. ठीक है, so rather than having 5 layers, now I will have only 2 layers. ठीक है, अच्छा, ये तो हो गया यूनिफॉर्म हाइट पे, यूनिफॉर्म क्रॉस सेक्शन पे। अब अगर हमारे पास कोई ऐसा फिगर है, सपोज हमारे पास एक ये ऑब्जेक्ट है जहां पर ये एक सेक्शन है, ये एक सेक्शन है और ये थर्ड सेक्शन है। ये थर्ड सेक्शन है। ठीक है, अब फर्स्ट सेक्शन पे ध्यान से देखते हैं। लेट अस अज्यूम इस पूरे पार्ट की हाइट है 500 माइक्रोन। ठीक है, जिसमें से ये हाइट आती है 300 माइक्रोन, ये हाइट आती है 100 माइक्रोन और ये हाइट आती है 100 माइक्रोन की। ठीक है, तो सबसे पहले हम लेते हैं 300 माइक्रोन वाला पार्ट। 300 माइक्रोन वाले पार्ट को जब मैं ऑब्जर्व करता हूं तो इसमें कोई चेंजेस नहीं है, इसके सारे डायमेंशंस फिक्स्ड हैं। ठीक है, सो व्हाट आई विल डू इज आई विल टेक 150 माइक्रोन इनटू 2। आई विल डिवाइड दिस इनटू 2 हाफ्स एंड आई विल take it 150 micron into 2. So this is my first part. Now second part में मैं क्या देखता हूं, इस एक्सिस पे इसकी डायमेंशंस चेंज हो रहे हैं। तो यहां पर मुझे पार्ट बहुत सोच समझ के बनाना होगा। सो आई विल बी मेकिंग द पार्ट्स इन अ स्मॉलर क्रॉस सेक्शन। सो व्हाट आई विल डू ओवर हियर इज 100 माइक्रोन की हाइट है। ठीक है, अब इस 100 माइक्रोन की हाइट को मुझे बनाने के लिए व्हाट आई विल डू इज आई विल टेक 25 माइक्रोन into 4 for second part. Now I have reached over here. So this is again 100 micron. Just in order to make it easier, I have 50 micron into 2 layers. So in total 8 layers, I will finish this part. So when I go about changing my layer thickness with respect to different characteristics or different modes of the part to be fabricated, this is what is called as adaptive slicing. Now, what happens is when you talk of adaptive slicing is actually something which is very tricky to understand. Why? Because the general conception is that when you go and do the slicing process, at the end of the slicing process, when you cut the layers, what you actually observe is a surface area. ठीक है, so this is a surface area that you observe. जो कि आपको मैंने अभी फिगर्स में भी दिखाया. Now when you see this surface area, we assume this to be a perfectly flat surface area. But actually what happens is something which is pretty different. The actual conditions are very different. What happens at the profile, edge profile, is something which is very different, and that is what has been modeled over here. Some people have assumed it to be rectangular, just like this. This is the rectangular profile. Some people have taken it to be trapezium. Some people have assumed it to be a parabola. Some people have assumed it to be a limiting area. What it actually is, I will show you, not today, but after tomorrow's class. After tomorrow's class. Okay, I will show you after tomorrow's class. Now, the whole concept of the edge profile is something which is very important to understand when you do slicing. The whole concept of edge profile is very important to understand during the slicing process. Why? Because what happens is the edge profile actually is going to affect your surface roughness. The edge profile is actually going to affect your surface roughness. Now, I'll just take the example of the second region and I will plot it over here. The second region I am plotting over here. This is the second region that you generally see, which will be depicted something like this to you. But actually, when you go and observe the profile is something like this. And that is why when you take your probe up upon this, there is a peak, there is a valley, there is a peak, there is a valley, and there is a peak. That is why you get surface roughness. So the whole nature of the edges actually also determine how the slicing procedure is going to be defined. So there were different concepts and different theories which were developed with time, and people came up with different ideas how the slicing procedures actually turned up. So when RP actually evolved, that is in late 1980s, like 86 to 89, basically, we didn't have the concept of adaptive slicing. We only had the concept of uniform layer thickness. So people used to just play with the layer thickness in such a way that if you have got any critical feature, like if I have something like this, so now since I'm going for uniform slicing, so I measure this distance, and then based on that, I define my layer thickness. Okay, so based on that, I actually end up having a layer thickness which might be feasible, which might not be feasible, where at the end of the day I might not even get a proper product or a proper replica of what I was trying to make because of my layer thickness. So adaptive slicing actually came in early 90s, like 92 and 93. It actually came in 92 and 93 to be very precise, and it basically revolutionized the whole concept of slicing, because now you didn't have to compromise on the part geometry and the RP machine specifications also. Now you were not bounded by the part geometry. You could take any part geometry, you can cut that into sections, and using those sections you could end up working with the models. Most of the people were actually focused on considering the edges as rectangular. Most of the people actually focused on considering it to be a rectangular profile. The edges were rectangular like this. But with new technology of SEM and other imaging techniques, when people started doing this research work, they ended up finding that definitely it is not rectangular. It is either trapezium or it is parabolic in nature. And primarily it is parabolic in nature. Even trapezium also, in very few cases they were found trapezium. Mainly it was parabolic in nature. So rather than having a specific layer thickness, now most RP systems have a range of minimum to maximum thickness. Like the machine that we have in our labs, you can start from 50 microns and go up to 2 layer thickness. So people started having a range basically now, and I have the flexibility of incrementing these values by 1 micron. So I can have a whole lot of surface layer thickness values with ranging from 50 micron to 2 So this is the basic idea. Now the cusp height concept actually came out during this same time, because the maximum allowable cusp height that was defined was actually considered equivalent to the surface roughness value. So, but please remember, for design or manufacturing, cusp height is not a standard parameter. It is not a standard parameter. It is a user defined parameter. Depending upon the edge profile that you have got, you have developed a facet, and with the help of that facet you have developed the concept. It is not a standard concept, but it is able to explain a lot of phenomena regarding surface roughness that happens during the processing. So you understand cusp height. So this is where I am stopping right now.